Now let us try to do the evaluation again, and this time you will see, okay, that's a pretty perfect graph. Now hey everyone, how are you? In this video, we are going to create the second project in our 50 projects PyTorch series. In this project, we are going to create a linear regression model on a real world dataset using PyTorch. We are going to cover topics like understanding about linear regression, loading our data and pre-processing our real world dataset. We are going to define our model, the loss function and the optimizer for the model. And then we are finally going to train the model and evaluate the performance of our model. We are going to use the diabetes dataset to predict the diabetes progression on a patient, and we are again going to use the linear regression model for this. So for that, first of all, let us understand a bit about what is a linear regression. Well, linear regression is one of the simplest machine learning model you can find, and that's for sure. And this is used for predicting a continuous value, not a categorical value, but a continuous value. It assumes that there is a relationship between our input and output, and the relationship is linear, right? And the formula for a linear relationship is y is equal to mx plus b. And in this formula, y is our target or output variable. So basically we are trying to predict the diabetes progression on a patient. So y will be the diabetes progression. X is going to be the input features. Now there can be one or more number of features. That is something we will see in the dataset. M is the slope, and in machine learning terms we call M as the weight. That is how much weight is this particular feature is having to predict my output. Now this formula is mx plus b, but in case you have more number of features, let's say you have 3 features, then the formula will be m1 x1 plus m2 x2 plus m3 x3 plus b. If there are 3 features, there is going to be 3 values of m, that is the weight, individually for each of the feature, and the values are going to define how much weight is that particular feature have on your output. B is your bias term, which is independent of any of your feature and is an intercept on your graph or on your linear line. Our goal will be to find the best values of M and B so that our linear model can predict the value of Y, which again is the diabetes progression which we need to predict for any given value of X, which is our input. Now that's all about the theoretical part. Let us go to our coding part and see how we can implement the code for this. We are going to see the step-by-step implementation, and the first step will always be to import the required libraries. And before importing, if you have not installed these libraries, you can install it directly in this Jupyter notebook. You can call the command pip install torch space numpy space matplotlib space scikit-learn. This is for sklearn, and this is your command. But since you are running it in Jupyter notebook, you need to prepend this command with a exclamatory mark. Now this is a command which will run on your terminal. Now run this code, and this will install all the required libraries and all the required modules for this project. For me it is already installed, so it will not take a lot of time, but for you it might take some time if some modules are not installed. Now once it is installed, now let us try to import these modules. First of all, import torch, which is the core PyTorch library, and then we need to import torch.nn as nn. This is the neural network module of torch which will help us to create our linear regression model. Then import torch.optim as optim. This will provide us the optimizer for our model, which will be helpful in our training. Next is import numpy as np. This is to handle all the numerical data in our code. Then we need to import matplotlib.pyplot as plt. Well, we are going to visualize our actual and predicted values in the last to see the performance of our model, and for that we are going to use this matplotlib module. Next is we need to have our real world dataset. So I'm not using any external dataset. I'm using an internal dataset provided by sklearn.datasets. So I can say from sklearn.datasets, I need to import load underscore diabetes. This provides us a dataset, and this dataset is about some patients for which we already know the diabetes progression. So we are going to use this dataset for our training and testing as well. And to split our data into training and testing, we are going to use from sklearn.model selection. We need to import train underscore test underscore split. Now this function will help us to split our dataset into training and testing. And we also need one more thing, which is from sklearn.preprocessing. We need to import standard scaler. Well, this is to scale our dataset. We will see why do we scale our dataset and how do we do it. But in short, if we scale our dataset, it is better for our training. So once you write this particular code to import your modules, run this code. So this is now imported. Next part is we need to load and pre-process our dataset. So our dataset is load underscore diabetes. This particular dataset has 442 data or samples. which has 10 features or 10 variables. These are the medical features of a particular patient like BMI, age, blood pressure, and some other features as well. And we also have a target, which is the measure of a diabetes progression of a patient. This is a numerical value, and our goal will be to predict the diabetes progression using the patient data. So we are going to create a model using this particular data. Then we are going to do some predictions on some test data using this model. Now we need to perform 4 steps. So let us do it one by one and try to understand it. First of all, we need to load our dataset. So let us call it as diabetes. This is equal to load underscore diabetes. Now this is going to load our dataset in this variable diabetes. Now the next part is we need to extract our features and the target. So for that we can say X is our features, diabetes dot data. These are our dataset or the features, and the output is going to be Y, which will be equal to diabetes dot target. Now we have our features in the X variable and our target or the output in the Y variable. And let us see the shape of our data first. So we can print X dot shape and print Y dot shape. Run the code and you will see it is 442, 10 and 442. It means in the X, which is our feature, we have around 442 data and we have around 10 features or 10 different columns. So these are our rows and these are our columns. This 442 means that we have 442 rows or data and just one feature. Okay, that is the output feature, which is diabetes progression for a patient. Now we need to split our data into training and testing as well. Okay, so because we have like 442 data, we are going to use this data set first to train our model and then to test our model. So we are not going to use all this data to train it, because then we will not have a data to test it on. We need to test our model on some new data which our model has not seen earlier. Okay, so for that we are going to split our data randomly into two parts. First one will be training data, second is going to be the testing data. So let's do it. First let's create X train. This is going to be our training data, and X underscore test. This is going to be our testing data. Now the output for training data is going to be Y train and the output for the testing data is going to be Y test. And this will be equal to train underscore test underscore split. So you remember we imported this from sklearn.model selection for splitting our data into training and testing. So this can help us to do it easily. So we are using this function. In the function, you need to provide few things. First, the features. So X is our feature data and Y is our target data. So X and Y we need to provide, and then we need to provide how much percentage of data do you want as your testing data. So we want it like 20% of the data can go for testing and 80% of the data can go for training. So test underscore size, this will be equal to 0.2. This means 20%. Okay, this is out of 1. And we are also going to assign a random state variable. This is going to be 42, or you can call it 40. We will take 42. Now this means that every time you are going to produce a data set using this function, it will be same. Okay, well, for now, for this project, this is not very much significant. This is used to provide a particular state to your random split. So once you provide a state, the split or the random split will always be same. Now we have done the splitting of our data into training and testing sets. Now we need to standardize the features. Now this is very important for a stable training or a good training to your models. So let me first standardize it and then I will explain you the code as well. So create a variable scalar, and this will be equal to standard scalar. Again, let me tell you that this is something we imported from sklearn.preprocessing for scaling our data. And I will tell you why do we scale it before we actually do it. So see, we have some data, right? We have data like BMI, age, blood pressure, right? Now the range of the values of these features are completely different. BMI is generally from 15 to 40, right? For a person it can be 15 to 40. That's the normal range. We have age, right? Age is generally from 0 to 100, right? Blood pressure can be from 80 to 120 to 160. And then there can be other feature for which the range can be 200 to 300. So the range of our data are completely different. And if the range is different, linear regression can try to put more weightage to a particular feature which is having bigger value. Now we don't want it, right? We don't want that our model is biased toward a particular feature. And for that, we need to standardize the values of our features into a particular range. And for that, we are going to use standard scalar, which is going to normalize our data in a particular range. So the range for all our data, all our features are going to be same. So first of all, we need to say scalar dot fit underscore transform. Okay. Now this fit transform will actually create the scaling factor in our scalar object. Okay. So first of all, we are going to fit our transform on our training data. Okay. So this is our training data, X underscore trained. Okay. We will use the training data to fit our transformations. Okay. Because testing data is something we have not seen, right? It is something we will not see during training. and right now we are focused on training our model. So we are going to fit the transformation based on the training data and then assign this to another variable, which is x underscore train underscore scaled. Now this is your scaled data. Okay. Now let us also scale the values of your testing data, and this time you will see what I am doing is x underscore test. This is going to be equal to scalar dot transform. We need to transform our testing data as well. But there is a very important difference. When we were transforming our training data, we used fit transform. Fit transform is doing two things. First of all, it is creating a fit based on the training data of what range and kind of scaling it needs to do. Okay. For scaling, it will calculate the mean, the standard deviation, and it will only use the training data because we don't need to fit our scaling based on the testing data. So fitting the scaling or fitting the scalar means we are creating the range for the scalar or the standard scalar based on the training data. And then we are using this scalar to transform our testing data. Okay. So the transformation on the testing data has happened based on what we have already seen, that is the training data. Now the scaling is done, right? We have standardized the features as well. Now the next part is we need to convert it to PyTorch tensors. Now this is very important. This is our data set and this is a NumPy data. Okay. We need to convert it to tensors, which are like your data holders or your containers in PyTorch. PyTorch works better on tensors as compared to NumPy. So we need to convert it to a tensor object which can hold our data, which is very simple. For that we can say x underscore train underscore tensor. This is our training data and this will be equal to torch dot tensor, and in this you can provide your actual training data. So this is our actual training data, the scaled one. So paste it over here and provide the data type. So the data type will be equal to torch dot float 32. Okay. So we have scaled our training data. Let us also scale our testing data, right? So we have converted our training data to tensor. Let us also do it for the testing data and also the output data as well. So let us do it. X underscore test underscore tensor. This will be equal to torch dot tensor, and we need to provide x underscore test, and the data type is going to be torch dot float 32. Now let me just copy this for our target values as well. So it will be y underscore train underscore tensor. This will be equal to y underscore train. So since we have not scaled the value of the target, so this will be y train, this one, and then again y test underscore tensor. This will be equal to y test, and this x underscore test will be x underscore test underscore scaled. Okay. So the feature data is going to be converted to tensors, and we are going to use the scaled value. For the output data, we can directly use the original values. Okay. So now we have four tensors: the training tensor and the output for it, and the testing tensor and the output for it. Let me run the code. And once we run the code, okay, we have this print statement over here. So I think we can now remove these print statements, or we can just comment it. Okay, and run the code. So now we have loaded our variables. Now let me reiterate that why did we split and normalize our data? We split our data to ensure that the model is being trained on a training data and will be tested on a data which it has never seen. Okay. Normalizing our data will speed up the training process, and it will also improve the accuracy of our model. And converting our data to tensors will allow PyTorch, basically PyTorch, to process our data efficiently. Okay. Now next part is the fun part. We are going to define our linear regression model. Okay. We are going to initialize our model, and before that you need to understand few things. See, our model is a linear regression model. We have 10 inputs, right, or 10 features, and we just need one output, which is the diabetes progression score of a patient. Now based on this, let us create a linear model. For that we can say class linear regression model, and we need to assign nn.module class as the parent class of my linear regression model class. Now this will ensure that this class is a machine learning model in PyTorch, and inside this we need to implement two important functionalities: def underscore underscore init underscore underscore self, and we will see what we are going to implement. And also we have one more functionality, def forward. So we need to implement two functions in this particular class, the init function and the forward function. The init function will be called when we create the object of our class. So basically this is going to initialize our model, and the forward function will be used to do the predictions. So whenever we need to do a prediction on our model, the forward method is called. Okay, we will see how it is done. First of all, the init function. So in the init we need to first say super, and then we need to pass linear regression model. This is our class, and we need to pass this to our super class. We need to pass the object of this class. Now this will make this particular linear regression model as a machine learning model. Okay, and we can say dot underscore underscore init, and that's it. This is very important. Now we need to create the object of our linear regression model. So we can say self dot linear. This is a feature name. This can be any name, but we will call it as linear, and this will be equal to nn dot linear. Now this linear means we are going to create a linear regression model, and inside this we need to assign two values. how much input feature do we have? 10. And how many output feature do we need? 1, right? So here we have defined the structure of our model. Next is, what do we need to do when somebody try to predict a value, and the value will be passed in the variable x. So how do you want to predict it? We can simply say return self.linear. Now this will point to this particular variable, and we can pass the value of x. This is going to do the prediction using the linear regression model, and we are going to simply return it. Okay, so that's it. That's our model. Our model is created. Let's also create an instance of this particular model. The model is equal to linear regression model, and then we can run the code. And once you run the code, you will have a model variable which is actually a linear regression model. Now this model will try to learn a relationship, a linear relationship between your 10 features and create one output for it. The next part is we need to define the loss function and optimizer for our model, and we are going to use the mean squared error loss and stochastic gradient descent optimizer. Now why do we need this? See, the first thing is MSE loss. MSE loss means mean squared error. Now this will measure how far our predictions are from actual values. So while training our model, we need to see how is our model doing, how far is it from our actual result. Okay, if our actual value is 3 and our model is saying it as 5, then it is 2 values apart from it, right? So the loss is 2. So we are going to calculate the loss every time, and based on the loss we are going to update the weights of our model, and the updation part will be done by the optimizer. This will update the weight of the model based on the errors we are getting. And also we will have a term called as learning rate. We will use the value as 0.01, and this determines at what pace do you want our model to learn about something. Okay, so related to anything, right? If you try to learn anything very fast or very slow, both have its own advantage and disadvantage, right? So learning rate is also very important. We will see about learning rate a lot in our future projects. Okay, so you don't need to worry about it. First of all, let us create the MSE loss. So let's create a variable loss. This is equal to nn dot MSE loss. Okay, this is your loss variable which is going to calculate your loss, and then you need an optimizer which will be equal to optim dot sgd, and inside this you need to pass the parameters of our model. So model dot parameters, because this optimizer is going to update the parameters of our model. And then we need to say lr is equal to 0.01. lr means learning rate. Run the code. Now we are ready to train our model. It's a very interesting thing to train our model. Okay, so let us try to do it. So we will see how our training will work. First of all, let us try to implement the training part. Okay, now if you want to learn about anything, you will do it step by step, right? For example, if you are an archer who is trying to shoot on a target using your arrow and bow, so what do? Do you try to learn about something like read a lot of books first and then shoot it? No, what we first do is, if you are shooting it for the first time, you will directly come with your stuff and then point on the target, and then you will hit the target, and then you are going to see, or your coach will see, how did you do in your first attempt without learning anything. And that's exactly what we are going to do with this machine learning model. Before we actually train it, let us actually see what is this predicting in the first attempt. Okay, so y underscore predict or pred, this will be equal to model. Let's call our model on our training data. So our training data is x underscore train underscore tensor. So when you call this, now you need to notice one important thing. Now this x train tensor is having around 350 data. Initially it had like 442 data, and when you did a split, it has around 350 data. All these 350 data are passed to this model one by one. Okay, all your data will be passed to your model one by one, and each time it will call the forward function or the forward method on your data, and it will do the prediction. And what you are saying, what you have defined in your model is, it will return the value using this linear variable, and this linear variable is equal to nn.linear, which is your linear regression class. This will accept your 10 data and produce an output. So initially the weights in your model are completely random. Okay, so when you do it for the first time, you have given it your data, it will try to do any random prediction. Now let us come back here. Now this will do the prediction and it will give you the output. Now based on the output, based on what you did by shooting on a target, your coach will try to, or you will try to understand how good or how bad you did, right? And most probably, if we are doing it for the first time, there will be errors, right? So let us calculate that error. So error is going to be equal to loss. Now we are going to make use of this loss, right? Loss variable or loss object is the MSE loss, and we are going to calculate it. We need to pass two things. What is the prediction we did, and what is the actual value which we were expecting. For example, if you scored around 2 points and the coach was asking for around 10 points, which is the perfect, right? So the loss is around 8, right? So that's the initial loss you will get. So we will see the loss. So y pred, and then pass your actual value y underscore train underscore tensor. Now next part is, once you have calculated the error, right, based on the error, our coach here, our coach is this loss function. Okay, this will try to guide us that hey, do it like this, shoot a little bit above, shoot a little bit right, something like this. You will get some training, right? So that's what we are going to do in the next step, which is error dot backward. Now this is going to compute something called as gradients. Now gradients means how much adjustment you need to do, in which direction do you need to move to make a better result. This is going to compute the gradients, and then your brain will try to process that data and try to do a better step, okay, the next time. And here our brain is this optimizer. We are going to say optimizer dot step. What this will do is, based on the gradients which it got, it will try to update the model parameters, which are like weights. Okay, whatever weights your model is having, it will try to update it. Now this is the training part. Now this is one step in your training, or one time you did a training. How do you do a training in real life? You don't do it one time, right? You will do it multiple times, thousands of times you will do, right? And even after that, you cannot say hey, you are perfect, right? It requires a lot of training, and not just one time we are going to do this process. We are going to do this process multiple times, and that is called as iterations. And in machine learning term, we call it as epoch. Epoch is equal to 100. Now this 100 means that we are going to perform 100 iterations of training. So epoch is equal to 100. Okay, and then run a loop for e in range epoch. Now this will run a loop for 100 times. Put this code inside this for loop. Okay, now this is called training your model 100 times. If you increase the value of epoch, this will be like training your model 1000 times. Okay, the more you train, the better it is going to do. So let us do it like 500 times for now. And let's do one thing. After every 100 times we do the training, we are going to calculate the loss. Okay, and we are going to see after every training, you will see that the loss is decreasing. Okay, it will do better. So for that, we can say if the value of e mod 100 is equal to 0. Okay, then in that case, we are going to print two things. First of all, we are going to print the epoch number. So we can say epoch, or the iteration number you can say is e. And in this iteration, the value of loss or the error, that is something we are going to get from this error variable. So that we can say this is equal to error dot item. Okay, we call this dot item function to get the actual value. Now there is one important thing to understand over here. What are we doing? We are doing the prediction. We are understanding the error, right? Based on that, we are updating our gradients. That is, we are getting advice from our coach that hey, you need to move right, left, up and down, whatever the advice you get. And then you perform a new step. Okay, your brain is processing some data, and then the next time it is going to do a new prediction or a new hit to the target. Now every time you hit your target, your brain should process the new information from your coach. So the first time you can hit left of the target, the second time you can hit right of the target, right? So the previous advice which you have got, you will have to ignore that advice. So how we can do it here is, so for that, in machine learning model or linear regression model, we need to forget about the previous gradient value. Okay, so we can say optimizer dot 0 underscore grad. Okay, this will make the optimizer forget about the previous gradient value, the previous advice which it got from the error, and every time it is going to take a new step. Now we can just run the code and this will do the training. Now you need to focus on the output. See the output, what the output says. The output is saying on epoch number 0, that is your first time you did try to do something or try to do the prediction, the loss is around 29,000, right? But after 100 iterations, means after learning it or doing it for 100 times, the loss is decreased to 6,491, right? And after every 100 iterations, you will see the value is going to decrease, right? It's decreasing. So now we have trained our model. Now this is not a perfect model. Okay, now if you want to make it perfect, what you can do is you can run more iterations. So let's actually do it. Let's run it for 5,000 times. You don't need to do it, but we can do it. That's an optional part. And now we print the error or loss after every 1,000 iterations. Let's run the code, wait for some time. Now you can notice one thing, that the loss is decreased to such a point that now after every 1,000 iterations also the loss is not decreasing. Now this means that based on the given data, this is the best this model can learn for now. What we did is forward pass. We made the prediction using the model, and this is called forward pass because we are actually using this forward method to predict the value. It is getting called internally. Okay, you don't need to worry about it. We calculate the loss. That means we measure the error in the prediction and compute the gradients for each of the weight of each of the feature. That is called the backward pass. Then we update the weights using the optimizer, and then we repeat the process. Okay, now let us do the evaluation of the model. How well did it do? Now you can see this conclusion part. If you want to reach this conclusion part, I will tell you that this evaluating the model is going to be really interesting. Okay, so we are going to plot a graph between the predictions and the actual values. For that, first we need to do a prediction, right? And to do a prediction, let's create a variable y underscore test underscore spread, and this is going to be equal to model. We are again going to call our model, but this time we are going to call our model on the testing data we had, right? And remember, our model doesn't know about the testing data, so it is going to see this data for the first time. And when we are doing the actual prediction, we don't need to compute the gradients, right? See, the computation of the gradients takes some memory, takes some power. So when we are testing it, we don't need to do it, right? So let us do one thing. We can say with torch dot no underscore grad. This means do not calculate the gradients. We are not calculating the gradients. Let's do the prediction. And let's also do one more thing. Once we do the prediction, we are going to convert this predicted value to numpy. This is because it will be easy for the visualization. So for that, we can say y underscore test underscore prediction. This is going to be equal to y underscore test underscore spread dot numpy. This is going to convert our data into numpy. So now let us plot a graph. For that, we can say plt dot scatter. We are going to create a scatter plot for our data. What is our actual data? Y underscore test. So this is our actual data, the actual value of the diabetes progression of a patient. But what our model predicted is y underscore test underscore spread. This is what our model predicted. Okay. Now to plot the graph, you can simply say plt.show, hit enter, and now you will see this is some scattered value. Now this plot is not perfect at all. We are going to make it perfect step by step, and then I am going to explain you how well our model did, right? Remember, we are trying to evaluate the performance of our model, right? So let's do one thing. Let's add something in our graph. First of all, let's add a color to our scatter plot. Okay, let's make it red. Okay, or let's make it green. That is going to be better. And let's add a label to it. This is going to be equal to predictions. Okay, so these are our predictions. Now once you hit enter, you will see this is better now. I mean, the color is improved, but still we don't have this label visible, right? Now to make the label visible, we can say plt.legend. Hit enter, and now you can see this legend is indicating that this green spots or the green dots are our predictions. But for now, this graph is not helping us to understand how well our model did. What's the actual value versus the predicted value thing. For that, let's do one more thing. Let us add a line in our graph, plt.plot. Okay, we are going to add a line, but first of all, let me add the line, and then I am going to explain you how this line will work. For that, you can say first data is the data in your x-axis is going to be y underscore test dot min to y underscore test dot max. Okay, this is your x data, and the data on your y is going to be same. Okay, so we are defining a range for our x and y in our graph. So right now we don't have a range, right? 50 to 300 is in the x-axis. In the y-axis, the range is completely different, right? So let us assign a range. Okay, now once we have assigned a range, we are also going to assign this a name. So label is going to be of perfect fit. Okay, hit enter, and now you can see there is a line, right? Okay, that's something I was not expecting. So I believe there is some error which we have done. Okay, let's get back to our data first. Did we did some error here? I believe we did, right? Okay, the first thing is, see, first of all, this should be scaled. Okay, I missed to add this underscore scaled over here. And second, very important thing I missed to tell you earlier was we need to say dot view -1 comma 1 and dot view -1 comma 1. And the reason is we need to reshape our data so that each value in the target is itself a column, right? So let me show you what I'm trying to say. So if I print the statement again, let me hit enter, and you will see that our x data is having 10 columns, but the y data is a single array, a one-dimensional array. We need to have each data in our y as a single column. So what we are doing is we are not changing the data, we are changing the shape of our data to have each value in a single column. So now if you will try to print the shape y underscore train underscore tensor dot shape, you will see that it's 353 comma 1. So we have 353 outputs for our training data, and each of the output is a single column, right? So now it is converted to two-dimensional array, and we are going to run each of the code again. So we are going to create our model again, we are going to create our loss function again, we are going to train our model again, and now you will see the training is something better. The loss which we were getting last time was around 6,000. After reshaping the data, the loss is reduced to 2875, right? So I think we did something better here. Now let us try to do the evaluation again, and this time you will see, okay, that's a pretty perfect graph. Now what's happening here is the perfect fit line is telling us what's a perfect prediction will look like. So let me add few labels quickly. Dot x label. The x label is the actual data, okay, actual data, or the actual diabetes progression. Okay, and then just copy the line, create a y label as well, and the y label is going to be predicted one. Okay, and now you will see that the x-axis is your actual diabetes progression. Okay, so now if our actual value is 50 and the prediction is also 50, so it will come on the line. Okay, now this line is telling you that what's the perfect prediction which will look like. So any dot which is touching your line is a perfect prediction, but if your dots are not touching your line, for example this one, it's a bit far away from your line, right? So this is representing a loss or the error in the prediction. So your actual value is somewhere between 200 to 250, and what is it is predicting is around 300. Well, it's fine, we do have a loss, but still we have some better predictions, right? For smaller values, you can see the predictions are better compared to the larger values. So this is something we can draw, and based on that we can improve the quality of our data and make our model better. And how did I draw the line? And that's also important to know. I used this plot method, and inside this you can pass your x data and y data. So my x data is from minimum to maximum of my actual output, and again my y data is same. Okay, so that's why the x range is 50 to 300, y range is 50 to 300, and now the plot has been done. And based on this plotting, we are able to draw some intuition, we are able to draw some output, right? So now I can say congratulations to you guys that you have successfully built a linear regression model using PyTorch, and we did some predictions on the diabetes progression. What you have learned so far is how can you load a real world dataset, you can split your data and normalize your data, implement a linear regression model using PyTorch, and also you can train it using the loss function and optimizer. We also saw the visualization and evaluation of the model, and we did saw how can we debug our code. If there's some error, we can debug our code as well, right? That's a very important skill for a good developer. Now guys, you can find the code of this particular project in the GitHub link, which is there in the description. Now, are you excited for your next project? If you are, then stay tuned for the next project. It will come very soon on this channel. And for that, if you're not subscribed to the channel, so make sure that you do subscribe to the channel. And if you did like the video, if you did like this project, then make sure that you hit that like button as well. And if you have some questions, if you have some feedbacks, then you can leave it in the comment box. And I will see you guys in the next video. Thank you for watching this video, guys.